Hello, this is Steve Groven, and today's topic is gravity. Now, if you need to pause or backtrack or even fast forward, go ahead. I do not mind. Let's start out. First off, I'd like to start out today with a few statements about gravity. Statement one, whoops, all matter has mass. Okay, let's kind of think about that. Now, statement two, gravity is a result of mass. And statement three, all matter is affected by gravity. Now, those of you who have had an algebraic background will notice that this is just like the transitive property of algebra. If A is equal to B and B is equal to C, then A is equal to C. Basically, it's a logic statement. All matter has mass. Gravity is a result of mass. So all matter is affected by gravity. All right, well, let's talk a little bit more about how this works. First off, a definition of gravity. It is a force of attraction between objects that is due to their masses. Okay, first off, I'd like to have a quick review of the term force. Basically, oops, sorry about that, a push or a pull exerted on an object in order to change the object's motion. Now, if you recall from from one of my earlier videos, gravity is one of the four basic or fundamental forces, which will, of course, gravity, discovered by Sir Isaac Newton. The other of the three forces are the strong forces, which is what holds atomic nuclei together. Electromagnetic forces, which of course is dealing with electricity and magnetism, and the weak forces, which is dealing with radioactive decay. Now, the thing about gravity is it has it basically has an infinite range, and it is always an attractive force. It is never repulsive. Gravity is never going to push you away. Okay, so let's start out by talking about Sir Isaac Newton. Now, according to the story, Sir Isaac Newton was kind of curious about an apple that had fallen from a tree one day. Some say it fell on his head. But he was not just interested in the apple, he was also interested in planetary motion, watching the moon going around the Earth, for example. So, from observing the apple and from observing the moon going around the Earth, he had two questions. First of which, why do objects fall? And the second, what keeps the planets moving in the sky? And from these observations, Isaac Newton came up with his law of universal gravitation. This is a law that brings together the ideas of force, mass, and distance in a mathematical formula. I'm going to bring that up over here, right over planet Earth. Force 1 is equal to force 2 is equal to g, which is a universal constant, multiplied by mass 1 and mass 2 divided by the radius squared, and the radius being the distance between the two planetary objects. Okay, so that's the mathematical equation of the law of universal gravitation. The two parts of the law of universal gravitation state that gravitational force is going to increase as mass increases, and gravitational force will decrease as distance increases. So let's see if I can't highlight here. So in other words, whoops, I think I didn't get that right. Okay, so as this, oops, that's not working. So as the distance between these two bodies increase, then the gravitational force is going to decrease. Also, as the mass of these two objects increase, the force is also going to increase. Let's take a look at that a little further, or a little bit closer. So what it's really stating that the greater the mass between the two objects, the greater the gravitational force. If you take a look at my little cartoon here, it's depicting four objects. The top two, small mass, So because they have a small mass, they have a low gravitational force. Then there are the two objects on the bottom have a larger mass, therefore they have a larger gravitational mass. Now, if we increase the distance between the two, the gravitational force is going to increase. Yet, just like in the top of the cartoon, but in the lower part of the cartoon, if you increase the distance, then the gravitational force is going to decrease. Now, the thing about this gravitational force, it occurs amongst all objects, between the planet, between you and your, bottle of pop that's sitting on the table. Every object that has mass is going to be affected by gravity. The thing is about the objects on Earth versus the objects that are out in space. Well, if we had a couple of objects out in space away from any planetary body and they were close enough, the gravitational force between them would pull them together. On Earth, on the other hand, the gravitational force between you and that teacup that's probably sitting on the table next to you, that gravitational force is insignificant compared to the gravitational force between you and the planet. Okay, let me move on to the next page. Let's talk about weight. Now, if gravitational force depends upon mass and it depends upon, let me just kind of pull up the definitions here. Three definitions. The first one is matter. Anything that takes up space and has mass. So anything that has some sort of volume and, of course, weighs something. In other words, it takes up space and has mass. So what is mass? The measure of material or matter in an object. Like, for example, my mass of my little brass weights there. I'm not sure if you can really see the lettering on there. I think the large one is about 5 kilograms. I'm not sure what the small one is, unless it's like 1 kilogram. But anyway, mass is the measure of material or matter in an object. Now, the thing about mass is it's going to be measured in the metric system. Mass is measured in kilograms, grams, and milligrams, and kilograms is the SI unit of mass. Weight is defined as a force exerted on an object's mass by gravity. Now, weight is measured in what's known as newtons, and the definition of a newton, 1 newton is equal to 1 kilogram meter per second squared. Now, I don't know if you remember our force equations, but the force equation is F is equal to your mass times acceleration. It's the same thing with weight. Weight is a force, so it's actually the same equation. Force is equal to mass times acceleration. Again, force is measured in newtons. The thing is, the acceleration in this case is known as gravitational acceleration. Okay, I've only got one more page left. So it was kind of a short, 8 minutes. That's not short. Okay, so let's continue on our discussion of weight as a measure of gravitational force. Now, the thing about the difference between mass and weight is that mass is not dependent upon gravity, but weight is dependent upon gravity. Let's take a look at what that looks like. Now, let's say we've got an astronaut that is standing on the Earth versus an astronaut standing on the Moon. If the astronaut standing on the Earth, well, in this case, our astronaut is weighed about 1,588 newtons, whereas on the Moon, it's relatively 1/6 the weight of that astronaut on the Earth. I mean, the mass of the Moon is that much smaller, so the attractive force between the Moon and the astronaut is going to be quite a bit different. So on the Earth, the astronaut weighs quite a bit more than he would on the Moon. However, the mass of the astronaut In this case, we use a balance scale to measure mass because we're comparing the mass of the man to a known mass. The mass on the Earth of the astronaut is 162 kilograms, but his mass on the moon is exactly the same. So the thing to take away from this is that weight will change depending upon your location, but mass, assuming that you haven't suddenly lost a lot of weight on Weight Watchers, your weight will change, mass will not change. And thank you for listening.